All right, in this video, what we're going to do is we're going to solve a problem that I have written out here. So we're going to find the frequency and the energy of light that has a wavelength of 656.3 nanometers. Now there's a couple things that I want to point out and kind of remind us because there's a few equations that we need to know in order to solve this problem. So let's first identify our equations that we can use. One of the equations that we know is that C equals lambda times nu. This is our wavelength, and our wavelength has units of usually meters. This right here is our frequency, and this has units of inverse seconds, and we can also call inverse seconds a hertz. So HZ for hertz. C right here is a constant, and this is the speed of light. And for our cases, we're only going to use that it's 3.0 times 10 to the 8th meters per second. If we wanted to be more exact, this number could be 2.998, so on, so on, so on. But for our cases, having this amount of exactness is fine. So we have this equation. We also have another equation for energy, and we have that energy, which is going to be in joules, is equal to H, this is a constant, times our frequency. So this is still frequency. I'm just going to put an F for frequency. This is a constant. I'm going to write this in a different color so we can kind of see it. It's 6.626 times 10 to the negative 34th, and this is a joule times a second. So that's what H represents. So let's go ahead and start solving this problem. I'm going to kind of put this off to the side. Now, when I first approach this problem, the first thing that I like to do is I like to convert my nanometers into meters. It just is easier for me to do that right off the bat. So if I were to do this, I'm going to say 656.3 nanometers. And I'm going to set up a problem because 10 to the 9th nanometers is 1 meter. Crossing out your units, you're going to set this equal to 6.563 times 10 to the negative 7th meters. So that's going to be my wavelength that I'm going to be using in these equations. So let's go ahead and solve for our frequency. Now, for our frequency, we do have this problem. We know our speed of light. We now know our wavelength in meters, so we need to isolate frequency. So C equals lambda times nu, but this is our unknown. So we're going to divide both sides by our wavelength, cancel that out, and we're going to solve for our wavelength, or excuse me, our frequency. So let's plug in our variables. 3.0 times 10 to the 8th meters per second divided by 6.563 times 10 to the negative 7th meters. Notice that you can follow your units. Your meters end up canceling out when you solve for frequency. And when you solve this, you get 4.571 times 10 to the 14th. And now this is inverse seconds, or we know that this could also be hertz. I'm going to keep it at inverse seconds because in the next equation, you'll see that it's really nice that the second actually cancels out. Do also notice that in this problem, my answer has 4 significant figures because I'm basing it off of the 4 significant figures in my original number. So this is the first part. This right here is our frequency. Now, based off of this, we can now solve for our energy using the equation that we have off to the side. So plugging things in, energy is going to be equal to H, which is a constant, so that will never change, 6.626 times 10 to the negative 34th, and this is joules times a second, times our frequency, 4.571 times 10 to the 14th 1 over a second. Notice that your seconds will cancel out and you are left with your units of joules, which are the units of energy that you want. So what you end up getting for your final part of this answer is our energy, which is 3.028 times 10 to the negative 19th joules. This is a 10. That got a little messy. So there is your final answer. So in this problem, a couple important things to remember. You need to know your equation, like this one right here, and you need to know what each of these variables represent, and you need to know which units they are. This is one of those things where I've mentioned before, if you want to create a flashcard with C and the speed of light on the other side. Have a flashcard that has what this symbol represents and the units it has, and have a flashcard with this equation on there. The other thing that you want to know is you want to know this energy equation. So have a flashcard with this. Now, on a test or a quiz, I do not require you to memorize H. So I will give you H, but you do need to know that H is a constant. So make sure that you actually have that on a flashcard and say that H is a constant. The other thing that you want to make sure that you know is looking at this and making sure that you have 4 significant figures in your final answer. So I am going to be looking for, do you have the appropriate number of significant figures? Last but not least, the last thing I want to point out is some things that can happen with your calculators because we are multiplying and dividing with significant figures, or excuse me, with scientific notation. It is really important that when you plug these things into your calculator, that you start to put brackets around things because your calculator will have a tendency sometimes, depending on your calculator that you have, to get the wrong answer, which means that you'll have the same base, but this exponent might have been like 1. And that's way too small of an exponent. So you want to make sure that you're putting brackets around things when you plug things into your calculator. So I hope this is helpful.